In this presentation, we're going to look at short columns. So these will be reinforced concrete members with both axial load and bending moment. So a combination of axial force and flexure. By the end of this section, I want you to be able to illustrate how axial load is going to change our moment curvature relationship, calculate the plastic centroid and the plastic neutral axis of a section, create an unfactored moment axial load interaction diagram and define the key points here. Describe how confinement affects the moment curvature relationship and moment axial load relationships of a column, and include the effect of tie spacing in the discussion. Create a factored moment axial load interaction diagram with the key points and include the minimum eccentricity limits, and calculate the factored capacity of a section with biaxial bending using the Bresler reciprocal method. Axial load is going to change the behavior of our reinforced concrete members in flexure. We can see below how our axial compression is going to affect our moment curvature relationship. Here we have a moment curvature relationship for a column with no axial load and an axial load equal to about 40% of its pure compression load. You can also see we're adding in some ductility greater than we would traditionally assume. So some of our ductility that we may get due to confinement. So we'll have strains greater than 0.003 shown here. What we can see is that adding an axial load is generally going to increase our strength of our unconfined section, and it's also going to decrease our ductility. The reason that our strength increases is because normally our flexure failures controlled by the yielding stress of our steel and tension. So when we're adding a compression load, we're kind of overcoming or offsetting some of these tensile stresses, which will give us an increased capacity. This will decrease our ductility though, because it'll often lead to a compression failure in our concrete happening earlier, which is a less ductile failure. We're typically going to look at the combination of our moment and axial load using a moment axial load interaction diagram, which is shown here. So normally our axial load is plotted on the Y and our moment's plotted on the X. Here we have compression above the axis here and tension below. So you can see that each point on this curve represents a combination of moment and axial load applied to the column that would cause failure. So these points on the curve would cause failure on this column. Load combinations that are outside the curve cannot be held by the column. So these load combinations would cause failure of the column. Load combinations falling inside the curve will not cause failure of the column. So these load combinations can safely be held by the column whose capacity is represented by this curve, the moment axial interaction curve. We can develop these moment axial interaction diagrams using the same tools that we used in flexure. So we can find any combination of moment and axial load just by using our equilibrium equations and our compatibility relationships and our constitutive laws. So we'll sum, in general, our internal forces and moments equal to our external applied forces and moments. So where before in our pure flexure members, we had the summation of our forces equal to 0 because we had no applied load. Now we'll have an applied axial load. So we sum our compression forces and our tension force and set it equal to our applied axial force. Just like in our flexure members, we can also find our moment by taking all of our force components times a lever arm. And in this case, we'll typically take our lever arm will be the distance between the center of our force component and the plastic neutral axis, which we'll talk about in a couple slides. Also note that the applied moment is related to the applied load applied at some eccentricity. So if we have some load that's applied at the plastic neutral axis and a moment applied on the section, this is equivalent to a lesser moment and a load applied at some eccentricity, or it can be equivalent to a load just applied at an eccentricity where our eccentricity times our load is equal to our initial moment. So these three load cases are equivalent, or the column would respond the same to all of them. The plastic centroid, or a plastic neutral axis, is the axis or point where when we apply an axial load at that point or along that axis, it's going to develop no moment. So when we apply the load at our plastic centroid of our section, it's going to cause no moment in the section. So we can find the plastic centroid considering the full strength of our materials. We first find all of our different force components where we assume that all of our steel has yielded. And we're going to assume that with our concrete compression force, we're going to use 0.85 times F prime C rather than just F prime C. And this 0.85 takes into account the difference between cylinder strength and in situ performance, or the behavior of our column in an actual column, or concrete in our actual column. And it also keeps us consistent with our stress block approximations that we'll use for all of our other column points. So you can see we have our three different components because we have 2 layers of steel in our concrete section. We can take our steel out of our concrete component if we want as well. So then we can sum these and find the total force, or the total axial load capacity. And our plastic centroid, or plastic neutral axis, is just the force times the distance. Here we're going to take the distance from the bottom to the center of the steel. For our first layer of steel, our concrete component, which the centroid is at the center of our rectangle, and the second layer of steel. So force times distance, sum them, divided by our total force, our total axial load capacity of our section. And that gives us our plastic centroid. Note that if our cross-section shape is symmetric or symmetrical, and our steel is symmetrical, then the plastic centroid is just going to be at the mid-height of our section. The final concept that we'll want to make in this introduction is related to ductility. The first thing that we'll reference here is a moment-axial load interaction diagram. And note that any straight line that comes out of the origin is related to some load being applied at an eccentricity. So if we apply a load P at an eccentricity of E naught here, we'll kind of progress up on this line coming out of our origin. So the slope of this line is E naught. Then at some point, we would reach a curve here that would represent when our steel would yield. So there's some combination of, or all the points that lie along this line are a combination of moment and axial load that would cause yield of the steel in our column. Then the next point, or this solid diagram here, would represent the failure of our column. So a combination of moment and axial loads that would cause failure of the column. So we can find our ductility using either a constant axial load or a constant eccentricity. So with a constant axial load, we're looking at what's the yield curvature and ultimate curvature when we stay at a constant axial load. So moving horizontal here. Or we can look at the yield curvature and ultimate curvature of a constant eccentricity. So moving out on this eccentricity line here from our yield to our ultimate point. We can use either, but we just need to note which one we're using. We'll look at more of our moment-axial load interaction diagram using an example here. So in this example, we're going to create a moment-axial load interaction diagram for the following section. The section has a height of 20 inches, a width of 12 inches, and we have 3 number 9 bars on the bottom and the top face, with a distance from the outer face to the centroid of our steel being 2.5 inches. We have a 4 KSI concrete and grade 60 reinforcement, so our yield strength is 60 KSI. We're going to find the following points. We'll find the 0 moment pure compression point, the 0 tension point. We'll find the balance point, the point where our steel yields when our concrete crushes, our tension controlled point, when the strain in our steel is equal to 0.005, which is our tension controlled limit for ACI. We'll have our pure moment point where we have no axial load applied. And then finally our 0 moment pure tension capacity. So you can pause the presentation now and note what slide you're on and go to the video for example 1. We can simplify our moment-axial load interaction diagram by only calculating several key points. And some of the key points that you should calculate are the 0 moment pure compression point, the balance point, the tension controlled point, and the 0 moment tension point. Another point that is important, but not as important as the other 4 here, is our pure moment point. And the reason that the tension controlled and balance points are both important is because in ACI, this is when we're transitioning from one phi factor for compression controlled and another phi factor for tension controlled. So this helps us when we're going for our factored moment axial load interaction diagram. Note that if you're going to simplify your interaction diagram and just calculate a couple key points, you want to connect all these points in the diagram with a straight line. This will be a conservative assumption, as the actual curve will be outside, but you just don't. If you're only calculating these points, you don't know where this curve is going to be, so you need to make conservative assumptions. We're next going to look at how confinement is going to affect the behavior of our short columns. We're going to use this section from before, which had the 20-inch height, 12-inch width, and 3 number 9 bars on the top and the bottom. Now we need to know some information on our transverse steel though. So we're going to say that we have number 4 transverse ties, and we're going to look at a few different spacings. So these spacings are going to change the way that our concrete's confined. You can see they're all pretty close, so we'll have confinement effects for all of our columns here. And we can calculate our rho sub s, or the reinforcement ratio for our stirrups, just by taking the total volume of our confinement reinforcement for one transverse tie, and dividing it by the total volume of concrete that's being confined. First, we're going to look at the moment curvature diagram with different axial loads and the same spacing. So here we have moment and curvature for our section with different axial loads related to N naught, which is the pure compression capacity of our column. And then here we have spacing. Our spacing is equal to 8 inches for all of these different axial loads that are applied. So what do you notice? The two things that I want to highlight are when we're applying an axial load, we're going to have a greater moment capacity before spalling happens. So here we have no applied load, and here we have 20% of the pure compression capacity being applied. You can see that as we increase the load more, we're going to decrease the capacity, but we still, even when we have 60% of the pure compression capacity applied, we still have a greater capacity than we did with no axial load applied. The second thing that you can see is looking at the post-Spalling behavior. When we have no applied load, you can see that we have an increased capacity that's happening here due to confinement. And when we have an applied load, you can see that the slope begins to go negative, and actually we will no longer get above the capacity before Spalling. And the more axial load that we have, the more rapid our decrease in our capacity after Spalling. So when we're at 60% of the pure capacity load, you can see that our strength is dropping off pretty quick. So we have a pretty large drop after we Spal, and then even more of a drop as we increase in curvature. Here is the moment versus curvature plot for a column with, this time, 2-inch spaced transverse ties, and with varying levels of axial load. So 0, 20, 40%, and 60% of our pure compression load. So what do you notice here? The two things that I want to highlight is the first, our spacing is not going to have any effect on our behavior before Spalling. So before we Spal, we have our unconfined full section, and after we Spal, that's when we start Spal off our cover. That's when we start having our confined core, and our confining reinforcement will start having an impact. The second point is that the closer spacing is going to give us more ductility post-Spalling. So you remember with our 8-inch spacing, our strength dropped off pretty quick. So with our 2-inch spacing, you can see our strength will kind of maintain on our confined strength will maintain with increasing curvature. So you can see that with our 20, 40, and 60%. We'll still have a drop in strength from our capacity before Spalling and our confined strength after Spalling, but we can maintain that strength for increasing curvature. Now we're going to look at the moment curvature diagram of our section with several different spacings and the same axial load. So here's our moment curvature diagram, and this is for an axial load of equal to 0, so pure flexure. You can see that our spacing between 2, 4, and 8 inches isn't going to have much effect on the behavior of our confined section after Spalling. And the spacing has no effect on our unconfined section. Note that in this case, an 8-inch spacing is still sufficient to confine our concrete here. If we decreased spacing even more, we would start to see effects on our moment curvature diagram. Here is the moment curvature diagram for a column with 60% of its pure compression capacity and 3 different spaced ties, so 2, 4, and 8 inches. You can see here that our decreased tie spacing is going to give us more ductility or allow us to maintain capacity with increasing curvatures. So here, unlike the column with no axial load, our tie spacing is going to impact our behavior. And the 2-inch spacing will allow us to maintain capacity with increasing curvature. We can next look at how confinement affects our moment axial diagrams. And here we're going to remember that confinement's not going to affect our original section. It's only going to affect our confined core. So here we have a axial load moment interaction diagram, MN diagram. And you can see our original section diagram shown here, where we have an EC, the maximum strain in our concrete that our section can reach is 0.003. And in our confined section, we're increasing that to 0.01. So you can see that with our original section, we're going to have a greater capacity in compression than we do in our confined section. And that's just because in our original section, we have more concrete that's going to resist our compression loads. You can see that our spacing, though, when a smaller spacing is going to allow us to get a higher maximum concrete or confined concrete strength. So we'll have a larger capacity in the compression section when we have a spacing of 2 inches. You can see that when we lose our core, it's going to shift our neutral axis, which is going to shift how we calculate our moments. So that's why the diagram kind of shifts here in pure compression. And you can get in a confined section a case where you can have your maximum moment with actually a negative load in some cases. So with this column, that's what we're getting. And you can see that the spacing doesn't affect the tensile strength because the tensile strength is controlled by the tension, by the yield strength of our steel and the area of our tension steel. So that's not affected here. But there is a shift here between our original section and our confined section, again, because we're shifting the location of the centroid of our neutral axis when we lose our concrete cover. So now we're going to revisit ductility quickly, because each of the above columns is going to have an associated ductility. And we can remember how we found our different ductilities. So our curvature ductility here is just our maximum curvature divided by our yield curvature. Since our actual moment curvature diagrams aren't going to be as clean as this, we can make a couple different assumptions, which we'll look at. The first is called yield ductility, and we'll look at that, and then another called equivalent ductility. And the last thing is there isn't like a set value, but in general, it's recommended that we have a curvature ductility of at least 4 to have good column behavior. Although some have recommended greater than 15 for some seismic cases and things like that. So the first option for finding our ductility is just by using the actual yield and actual maximum curvatures from our moment curvature plot. So here we have some moment curvature plots for 3 different columns. And to find our yield or our curvature ductility using the yield ductility method, we would just take our maximum curvature from each of these and divide it by our yield curvature. We can see that using this option, we would overestimate the curvature or the curvature ductility in the first case here, and we would more accurately estimate the curvature ductility in these last 2 cases. And this is all dependent on how close your moment curvature plot is to the elastic plastic moment curvature plot that yield ductility represents well. So on the left, this isn't that close to elastic plastic, so it overestimates the curvature ductility. And here, it's somewhat close to our elastic plastic case. So, these well represent the actual curvature or curvature ductility. The next option is what's called the equivalent ductility method. And with the equivalent ductility method, we come up with a hypothetical yield curve based on the area under the curve. So essentially, we're trying to come up with an elastic plastic hypothetical curve where the area under the curve is equal to the area under the actual moment curvature curve. So what we do is we use the actual M max and we use the actual phi max or max curvature, and then we adjust our yield curvature so that we get our areas to be the same. So then when we find our curvature ductility, we would just take our max curvature, our max actual curvature, and divide it by our equivalent yield curvature. That gives us the same area under our moment curvature plot. We'll see that the equivalent ductility method is going to do a good job of estimating the curvature ductility for any moment curvature behavior. So it can be used in cases where the moment curvature plot doesn't look like an elastic plastic case. So one main observation to highlight is that we want to try to design our columns so that the balance point axial load exceeds the design load. So we want our load combination here where our NU1 in this case is below our balance point. And what this does is it makes sure that if there's any kind of accidental overload, so any accidental load that causes an increase in our axial load past what we designed for, moving up here is going to increase our moment capacity. So it'll just ensure that this point never crosses over our failure envelope. Designing below our balance point also ensures that we have some kind of ductility still in our column. So you remember that as we increase our axial load, we decrease our ductility. And we also decrease the capacity of our column. So if we try to stay below balance, so around 20 or 30% of our pure compression capacity, then we'll ensure that we have the maximum capacity in the section, and we also still have some ductility left in our section. We're next going to talk about a couple ACI limits for the design of reinforced concrete columns. The first ACI limit is for circular columns. We need to ensure that the confined strength of our column is equal to or greater than the original strength of our column with our cover. Essentially, this limit makes sure that we don't lose our cover and then immediately have our column fail. So it gives us some post-spalling ductility for our column. We went through this derivation before, so you can go back to the previous module to look at it again, where we talked about confinement material specifically. But you can see that ACI expresses this design limit as a reinforcement ratio required for our stirrups, our spiral reinforcement. So we need to make sure that we provide enough spiral reinforcement so that our confined column has an equal to or greater strength than our unconfined column with the cover. The next ACI limit that I want to just mention briefly, because again, we already discussed it, is the capacity cap that takes into account minimum eccentricity. So it's very difficult to apply a load directly in the center, at the plastic centroid of a column. So if we apply the load even the slightest bit off from the plastic centroid, we're going to cause some moment in our column. So what ACI does is it will cap the pure axial capacity and compression of our column, assuming that there will be some kind of minimum eccentricity, just based on tolerances. So this cap is dependent on if we have spiral reinforcement, we need to reduce our pure axial strength by 15%. And if we have tie reinforcement in a rectangular column, then we need to reduce our pure axial compression capacity by 20%. So these will be caps on our moment-axial curve, which we'll look at in the future here. The other point to highlight here is the ACI strength reduction factors. So these reduction factors are going to be dependent on the strain in our tension steel. In our flexure members, we're almost always going to be tension controlled, so we will almost always have a phi of 0.9. In our columns, because we're adding axial compression, it's much more likely that we have a steel strain at failure that's less than our 0.005. So we can be in the transition or even the compression controlled region for columns. So essentially what we'll need to do is we'll need to calculate our strain and compare our strain to the yield strain. If the strain in our tension steel is less than our yield strain, then we'll need to use a phi factor of 0.75 if we have spiral reinforcement, or 0.65 if we have any other type of reinforcement. So we'll typically be in this other region with our rectangular sections. And then if we have a strain greater than 0.005, we're still tension controlled. So we'll have a phi of 0.9, regardless of what type of transverse reinforcement we have. And if we're between 0.005 and our yield strain, then we'll vary linearly between these two. And there's an expression to help us vary linearly between the two. When we apply our phi factor, we apply it both to our moment and our axial load. And we also need to cap the axial load portion based on our minimum eccentricity limit. So you can see here we have our unfactored moment-axial load interaction diagram for the column that we've been looking at. And then we have our factored curve. So you can see our cap here will give us a horizontal line equal to the strength, the pure axial strength, including our phi factor and the, in this case, the 20% reduction for the rectangular tie section. And this is for our minimum eccentricity limit. Then you can see the difference between our factored and unfactored curve is greater on the compression side because we're reducing the strength by 0.65. Then on the tension side, we're only reducing by 0.9, so our factored is closer to our unfactored diagram. And then we have the transition region between our balance point here and our tension controlled point here. So you can see that the shape of our curve ends up looking kind of like a bottlenose dolphin because of the lower reduction on the tension side, the greater reduction on the compression side, and the transition between our compression controlled and tension controlled section. When we're designing, we want to make sure that our demand points from our different load conditions fall within our factored moment axial load interaction diagram. So here, if we had 4 different demand points from different loading conditions and they fell within our curve, we know we would have a successful design because we're designing our column to resist all of these loads. If we had one of these points falling outside of this curve, this would mean that our column is not satisfactorily designed for that load combination, but we wouldn't expect it to fail because it's still within our failure envelope. If we had a point falling outside both curves, then we would expect that point to cause failure of our column, and our column's not designed for that load. We can also have columns that are loaded to cause bending about both the x and the y axis. So if we apply the point of our load application with some eccentricity in both the y and the x direction away from our plastic centroid, then we're going to have a moment in the x and the y direction. So we need to be able to account for these biaxial loaded columns, which we're going to talk about on the next slides. we can use what's called the Bresler reciprocal method as recommended in ACI. And what this says is it says that 1 over the axial load capacity of the overall section. So if we were looking at applying phi Pn at this point with an eccentricity in the y and the x, and that's going to be equal to 1 over phi Pn x, assuming that we only have the x eccentricity and looking at the moment and axial load in the x direction and seeing the phi Pn x that the column can carry, plus 1 over phi Pn y, so isolating the eccentricity in the y direction, and then subtracting off the pure compression capacity of the column, assuming that we apply the load right at the plastic centroid. So if we use this equation, we can find the capacity of our column, so the factored load that we can apply with eccentricity in both the x and the y directions. We'll practice everything that we've learned with this example problem. So for this square column, that's 12 inches by 12 inches with 8 number 6 bars and 2 inches from the outside of our column to the center of our steel. Grade 60 reinforcement, 5 KSI compressive strength for our concrete. So for this column, we're going to construct an unfactored moment-axial load interaction diagram with our 5 main points. Then we're going to construct a factored moment-axial interaction diagram, both with and without our minimum eccentricity limit. And then finally, we're going to determine the column capacity if there was an eccentricity of in the x direction of 3 inches and in the y direction of 4 inches. So we'll use the Bresler reciprocal method for this. And at this point, you can stop the video and go to our example problem 2. Shown here are some references for further study on the topic of short columns.